Right then, welcome to your tutorial on these things here. Okay, proto boards or breadboards. Okay, in the lab we like to call them breadboards, depending on where you go. Sometimes they're called proto boards, sometimes matrix boards, sometimes universal boards, but we like to refer to them as breadboards. I guess the first thing we need to understand is how all these holes are put together. So if you actually connect up a circuit on these wrong, as you can see here, you can actually cause your components to short circuit or overheat and melt this piece of plastic. Okay, a couple of examples of that. Just saw that one. I've got another one. If I can find it on here, you can see just up here someone's embedded melted a chip into the board, and I believe, yep, over here someone's actually managed to melt some other components here, probably a transistor or something, or overheated a resistor, and actually melt these. So it's a good idea to find out how these are connected together. Now, each of these holes, okay, let's take this one because it's in my hand. Okay, each of these holes are all connected together in some form or another in order to build up circuit boards on them. Now then, how do we know what's connected to what? Well, that's why we use and why we have a trusty multimeter. Okay, so let's do some tests. Find out what pins are connected to where. Once we work out how the breadboard is laid out and what holes are connected, we'll go on and we'll draw out a little map on a whiteboard or something and try and relate that to a schematic, a circuit diagram. So let's do that. Now then, as you can see, I've got my breadboard here. First thing we need to do, switch on our multimeter, and you want to change it to the continuity checker. Okay, so when we touch our probes together, you can hear a nice beeping sound. That means that we've got two probes joined by a metal conductor, essentially something with a very, very low resistance. It's a direct connection. Okay, it's measuring connections. So let's start off with these tracks. Okay, they're all labelled. All these columns down here are labelled 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to 23. So each column is a number. Each row is represented by a letter in this case on this breadboard. So we'll plug in this one into here, A1. And we'll plug in another wire, say over here on A23. Okay, so let's see if we've got a connection from this point to this point. Two wires, two probes on breadboard, join them together. Oh look, no connection. Try it on the opposite corner, and behold, we do have a connection. This tier 1 all the way down to the bottom. No connection. So what have we found out? Well, we've found out that this row isn't connected to each other, these aren't connected to each other, but all of these are connected to each other. So let's draw that. So there we go, we've got one row that is connected together. Are these ones connected together? Yes, they are connected together. So this row wasn't connected to this row, but this row, this column is connected to this column, so there must be a connection there. So that's what our breadboard looks like at the moment. Okay, something like that. We've got two conductors. Next row along, or column along, not connected. connected. Again, not connected, and we are connected. So again, it's the same thing again. Okay, so we can assume that since that none of these are connected together, these are all connected in this direction. They all look the same. Well, they are the same, believe it or not. So we've got loads and loads of connections all up and down these. It looks something like that internally. Okay. But what about these outside holes? Well, we've got rows, so 1, 2, 3, 4, 5 holes, then a break, and 1, 2, 3, 4, 5, and then a break, 1, 2, 3, 4, 5, then a break, and then same down the sides. So are these connected together? Right, well, they're joined in that direction. Are they joined down to your circuit board in any way? No, they're not. Are these rows all joined together? Yes, they are. Are they joined down here? The corners? No, but they are joined. Let's assume that they're all connected across, all the way down, since that they're connected all the way across, and yes, they are. So they're all connected that way. You've got a line that's connected all the way down there. It's a pretty simple way to check a breadboard. Alright, well, let's draw out what this breadboard looks like a little bit neater, and try and relate it to a circuit diagram and how to build a circuit on these. Right then, drawing out my basic connection diagram of this breadboard. Okay, so we've got all our columns joined and broken in the middle, joined and broken, joined again, there's a break, joined again, a break, joined again, a break, and so on, and the outside connectors. Okay, what we call the bus bars, and this is what we call our design area. Okay, a circuit area. So how do we relate this to a circuit? Well, let's take a simple circuit, 2 resistors in series. So we've got our positive, what's our negative, 1 resistor, 2 resistors, all the way back to our positive. Okay, doesn't matter what value they are, it's just a simple one for building a circuit. Okay, so you've got 2 resistors, positive and negative, a couple of wires. Right then, so what do we do? Right, well, first off, these bars around the edge, this is what we normally connect our power to. Okay, so one could be plus, one could be minus, one could be 0, one could be, I don't know, we've got one plus 15, the other one could be a plus 5. Okay, another one could be minus 15, and you could have 0 somewhere else. Okay, normally 0 would be to the bottom, positives to the top. Okay, basic convention, inputs to outputs, left to right. So let's say, right, well, we've got our positive terminal, let's connect this to here. Okay, top of our breadboard. No, that's in actual fact the bottom of our breadboard. This is the top of our breadboard, isn't it? Okay, so we say, right, we'll have a wire going to the top of our breadboard. It goes to the positive terminal. Wire going to the bottom of the breadboard. Let's say it's our negative. Okay, so we've got our plus and negatives. Positive goes to one end of a resistor. It doesn't matter where we place it, we can have one end with a wire going from here to this track here. Okay, from the positive rail down to our negative rail. And we'll have our resistor leg of our resistor plugged into the same rail because we want them joined together. And the other one going into a next rail. Okay, as you can see, there's no wires joining these two sides of resistors together. There's no connection connecting these two because it's actually broken underneath this resistor that we just put here. And we can do the same thing again with the next resistor. We want to connect this resistor to this one, so we can pull it into the same connector. here. Okay, so they're joined with a little metal contact. There's a resistor. We can put that into our next one. Okay, our next row. So it's not connected here either. Over here, another wire which goes down to our negative rail. Another wire which goes down to our negative rail. Simple. And of course, it goes off to our negative terminal, which is a little power supply here. Crocodile clip leads. Okay, little dials on there, nice display. Okay, something like that, very simple. And that is exactly how you connect it up on here. So we've got positive wire going into positive, so plug that into there. Negative black going into our negative rail. Place a resistor across this bridge here, and place a resistor into there. Now you only have to push down very gently on these components. Okay, don't push them, force them all the way into the holes. Okay, otherwise they'll spread and potentially cause short circuits on the connectors underneath the breadboard, and I'll show you that in a minute. Okay, that's one resistor in here. Do I have a resistor on here? I don't actually have a resistor. I've got something that looks a little bit like a resistor. Okay, so I can actually place that one. And here's actually a diode, but hey, okay, this is just an example. And not forgetting, so we got this component connected from this row, which is this leg here. This leg goes into the next one down, which is here. We've got another component and the same one here that goes down into the next one. Got a wire which goes from here into the bottom one. Not forgetting to connect these, and not forgetting our little positive connector. The wire from positive. Let's do this one from here to positive rail. Something like that. Very simple. So we went from that to that to this little circuit here. We've got a component there, we've got a component there, wire connections, positive, negative, exactly the same as over here. Very simple. Alright, so back to the beginning. Okay, now not all components like resistors, diodes, inductors, so forth have two legs. Okay, you get components with multiple legs. So what do you do with components with multiple legs, like things like chips? We've got an amplifier there, we've got a digital chip there, I've got a little pop. Okay, little variable resistor. Okay, each got legs, and none of them should be connected together. Okay, right. Well, all through-hole components should have a set standard pitch of 2.54 millimeters, and the breadboard, the holes on the breadboard, are set apart by 2.54 millimeters. So these little chips here and components and other components should fit nice and square into a breadboard. They're not going to fit diagonal, just to prove that. Okay, they actually fit either horizontally or vertically, so that gives you a big clue on where to place them. Now, as I was saying before, with a nice little drawing, okay, board is laid out something like this, yeah. And the problem with, say, a dual inline chip is that it has 8 legs, okay, 4 on either side, and each leg has to be separate from the other leg. Okay, just lost that chip somewhere, so there we have it. There's another chip, okay, and that's a 74LS73. It's a digital chip, TTL logic. Now then, if each leg has to be in its own, isolated from each other in order to work, okay, you definitely don't want them to connect together, otherwise you can cause short circuits. Each one of these has to be in its own individual column. So, if it was connected that way round, you'd actually short circuit all of the legs on either side together, because all of these holes are connected vertically. If you connect it across that point, then, because it's all connected firstly, two of the legs will be connected together. So there's only one real place left where this can be put. It can't go across the centre because it's too wide, but it can go across the middle. Okay, so like I was saying, if you put your chip that way round, you'd short out the pins running down the side of your chip. If you placed it across the row, then you'd short out pins on either side on each column, so every side of the chip will be shorted. So what you need to do is you need to place it across a break in the track, so each pin has its own column. Okay, so each pin is in its own column. They're not joined underneath the chip, they're not joined in between. Each one has its own column to connect to. Very simple. Exactly the same goes with these devices, these variable resistors. Okay, if you look at the bottom, okay, 3 pins, okay, each has a separation of a multiple of 2.54. Yet again, that magic number. Okay, why 2.54? 0.1 inches. Everything related from the inch is what we started off with, so everything is around that number, but now we've gone over to metric. It actually worked out to 2.54. That's the magic number, as it were. Just like with the chip, each leg has to go in its own individual row or column, and it can only go either horizontally or vertically. You try and place it diagonally, it just doesn't want to fit. Okay, again, it just doesn't want to fit, not unless you start bending pins. If you bend the pins, well, they're going to snap eventually, and the whole point of using breadboard is that you can unplug the components so you can use it again. Okay, there's no soldering needed. Saves you a hell of a lot of money. You have to build, say, 10-12 circuits, each one using an op amp. £1 each, that's £12 per op amp. First, £12 in total, £1 per op amp. Or you can just reuse the chip. £1, and you can build as many circuits as you like. Hey, done. Same goes with pots. Okay, some of these can be a little bit more expensive than chips, but like I said, they can only go one way. In this case, it can only go horizontally, because if you connect it vertically, okay, you're going to end up shorting out, connect together the 2 pins. Okay, you don't want to do that, because you'll short out the component, it's not going to work properly. You want to connect it so it's in each individual column. There's only 3 pins on this. Okay, there's none next to each other, so it can easily fit into a column. Okay, nice, snug, secure. If you did try and force that so it wasn't square, as you turn the pot, your base would move as well, and this would just pop out of the board. So it's good practice to make sure that you're connecting things horizontally or vertically. Even if you take a look at PCBs, printed circuit boards, all components are usually either horizontal or vertical. It's very, very rare that you find one diagonally placed, because it's another process, you know. Your pick and place machine, if it's going to be placed automatically with short legs on components and what have you, or if you get someone hand soldering in them, you don't want them having to orientate the board around all odd angles in order to get all the components in. It's a lot easier and a lot quicker just to do your figure up that way or that way. Job done. Okay then, as I said before, okay, these are all connected with metallic contacts. Okay, so if we flip this board over, what I've done is I've actually took the bottom off this one to actually show you. All of these contacts are actually horizontal or vertical or horizontal. Okay, so we had all our holes, and underneath all the holes there is a metallic contact underneath, and if I pop one of these out, I'll show you what they are a little bit closer. As I was saying, try not to push your component in too far, because what can happen is if your component leg sticks out the end, okay, say on this one just here, okay, you might stick out the end and it could touch the one on the opposite side and create a short circuit between the two. Okay, so it's always good just to use a smaller, say no more than 5mm of insulation or so removed, so when you plug it into the board it can't actually skip into any of these other branches. Now these metallic contacts look like this. Okay, can you see that? There we go. That's what they look like inside. Okay, they're spring-loaded clips. Okay, now depending on how expensive you want to pay, how expensive your breadboard is, how much you want to pay for it. Okay, these contacts can vary. Okay, these ones are actually silver coated. Okay, to give you a very, very good contact resistance. Okay, conductivity is very, very good on these because they're silver coated. Other ones, they're bare copper. They can oxidise over time. They're pretty cheap. Okay, instead of paying, I don't know, £10 for a breadboard, you'd only pay, I don't know, maybe £2-3, maybe less, 50p. Okay, but trouble with, if they're not coated, okay, you just use bare copper ones, the copper will oxidise and then they'll give you a very, very poor connection. Okay, so you can get the copper ones, but don't expect them to last. Okay, pay out for a good decent breadboard if you're going to be using it. Okay, you can, like I said, these ones are silver coated. You can get nickel coated, you can get solid nickel ones, you can get gold coated if you actually want gold. I wouldn't recommend you getting gold. It's a waste of money in my eyes. Okay, for breadboard, it's a universal. They're not the greatest things in the world. It's pointless spending hundreds of pounds on a bit of breadboard when one about 10 quid will do the same job and it'll last exactly the same length same amount of time. So that's what's inside them. If we show you from this side, okay, now on these clips, okay, it's quite important that you don't force the wrong side wire into these holes on the breadboard, because what you can actually do is you can actually distort these. These are spring loaded, but if you bend them with the wrong size wire, you can actually bend them out of shape. Okay, just like that. It doesn't take much, so try not to force the wire into these. Okay, don't push super huge long wires in, because it can cause problems, creating short circuits. Use a sensible size. Okay, you can't go wrong. Now then, moving from this one, like I said, you can get breadboard in different sizes, different shapes. Okay, just like this one, all the layouts are more or less the same. So it doesn't really matter what breadboard that you get yourself. Okay, as you can see, it's still got this split row in the middle for your chips. Okay, just like it's got the split rows here. This one's actually got two. This one's just got one. It's got your bus bars along the top, just like it's got your bus bars around the edges on this one. It's got top, bottom, and all your interconnections are all vertical connections. They're all exactly the same. These have got 5 holes. This has got 5 holes. Same amount, same pitch. No difference. Looks different? once you learn one breadboard, it doesn't matter what one you go and buy. It's exactly the same. You just pay for it's all pounds and pence for what you actually want, really. The more you want to pay out, the bigger the breadboard you get. We've got this style of breadboard, very similar. Okay, it's just that your bus bars are all at the top on this one, and you've also got some. This one's actually made up similar to this one, where you've got the tabs where you can slot multiple ones on to make up huge arrays of breadboard. This one's actually all connected up for you. It's also got some screw terminals across the top, which leaves us with this breadboard here. Okay, this is the one that you use in the lab mostly. We do have lots of these little yellow ones. Okay, as I said before, make sure that you connect up all your components around the right way, because these are actually, some of these are actually damaged as well. When you come to using this breadboard, okay, I recommend you do similar thing to this one, what we did with a multimeter. Do a couple of continuity checks, find out what wires are connected to what. Okay, on this breadboard it actually helps you because it's actually got the bus bars here, and it shows you a line. Okay, so you can make some fairly educated guesses. Okay, so you got A, B, C, D, E, F, G, H, I, J, same thing going down, so all your columns and rows are all numbered and lettered. Colour coding set standard. Okay, so it's even colour coded, so you can have the red, connect the red wire to the red, black to say the blue, and you can't go wrong because the colour coding follows through. Okay, now like I was saying, on these ones, instead of on this one, okay, where we had plus and minus connections, okay, we had plus and we had minus in our circuit diagram, and we connected plus to top rail, negative to the bottom rail. Okay, on here we've actually got terminals, so you can actually screw, instead of having a floating wire on this one with a crocodile clip or something hanging on the end, which can create short circuits when they touch to each other. On this one we've got screw contacts, so you can actually plug your 4mm wires into the top of these and just have a small wire which you actually screw into the bottom. And if I unscrew this, you can actually see, okay, you can see a hole, just about. Okay, in the terminal, put your wire through the hole. Okay, strip your wire, put the metal conductor through the hole, screw it down, and you have a nice secure wire going to a 4mm terminal that you can plug down throughout these boards. Now on here it's got ground, V1, V2. Okay, so you can add positive, negative and 0. Okay, try and follow the colour coding so we know what's connected to what. Always useful. Okay, and on this one, okay, as you can see, the bottom's all fully insulated, so you can whack this down on your desk or you don't have to worry about what's underneath your board. To an extent, you have to worry about what's underneath the terminals, what's underneath these, but they're pretty well insulated. And like I was saying before, chips still only connect around so far. Now these boards are quite large, okay, and as you can see, I've got a 14-pin chip. You can fit tons of these across these middle ones. Okay, so what I'll suggest you do is try and utilise the space. Okay, if it's a large circuit, start with your inputs, say on start with your inputs on this side, work your way along, outputs on this side. Simple. Power at the top, feeds in from the top to the bottom. Ground always to the bottom. All your positives dotting down. Maybe ground in the middle if you've got a negative. Okay, so 0, negative, positive. Try and keep to general conventions as such. And that is your breadboard. There's not really much more to say on it, except all you can do is practice. So keep practicing, and eventually it will become second nature to you. But like I said, for the first couple of circuits that you ever do, draw out your schematic, translate that on paper onto a layout on your breadboard. So draw your columns and your rows of your breadboard, and just draw on there, draw your components on there. That way you can tell whether you've got any short circuits. How do I connect up a chip and put it across there? How do I connect up a resistor? Well, I'm going to jump across tracks or columns to make sure that the pins aren't connected together. Simple. Just come into the lab, have a play, and the more you play with these boards, the more circuits that you build, the easier they become. Okay, like I said, breadboard, prototype board. Always best to prototype your things. Never go to your PCB straight away. Sometimes you can't help it with surface mount, but these aren't too bad. But the only thing that I have to warn you about is don't try and use frequencies that are too high. Okay, once you start hitting the megahertz range, breadboards aren't as good as you might think. Okay, and why? Well, they're two metal parallel conductors separated by plastic, and I'll leave you to ponder what component that is and why high frequencies don't run on breadboards.